Hello and welcome to the online lecture for General Physics 2 dealing with Kirchhoff's laws. Kirchhoff's laws are two ideas that can be used to analyze electrical circuits in any case, but often what we do is we end up using Kirchhoff's laws when we discover a circuit that can no longer be analyzed with the ideas that we've built up so far dealing with Ohm's law and how to combine series and parallel resistors. So here's one of those circuits. Imagine you have this circuit. It's got 4 resistors in it, what's new is that it now has 2 power supplies in this particular circuit. We would like to figure out, how much resistance this is, how much current is going through various parts of the circuit, what the potential difference is across various circuit elements. And so specific to this particular circuit, we want to find how much current is going through this 2 ohm resistor down here, and what is the potential difference across this battery that is in the lower part of the circuit as well. Well, if we start thinking about can we apply Ohm's law to this, can we combine series and parallel resistors? Well, the 2 resistors that are in the top of this circuit can in fact be combined. They're series to each other in the same amount of current. That 3 amp current is going to go through both of them. But then you get stuck because that combination is not in parallel with either this 6 ohm resistor or this 2 ohm resistor, because you won't have the same potential difference across those resistors, and then you don't really have anywhere to go. We need more general rules for analyzing circuits of this nature, and again, any nature, but specifically ones that we can't analyze with the tools we've introduced so far. So I'm switching over to a couple of questions about your everyday experiences. As always, when we have these questions in the discussion, I would encourage you to pause the thing and come up with an answer before you listen to what my response is. What can you say about traffic in any intersection? Here's an overhead shot of traffic in an intersection. More traffic enters than leaves, more traffic leaves than enters, or an equal amount of traffic enters and leaves? Well, if the intersection is functional, you better hope that it's number 3. If more traffic enters the intersection than leaves, then you are building up cars within the intersection, which will quickly clog the intersection and no more traffic will be able to flow. If more traffic leaves the intersection than enters, somehow you're creating cars in the middle of the intersection or something of that nature. An intersection, a junction of 2 roads or more, is simply a place where traffic enters, traffic exits, and the same amount enters and exits, even though different cars may go different routes. How about this? If you walk around a city block and get back to the starting place that you were originally, what can you say about your elevation change in walking around that city block? You'll experience a net elevation increase, experience a net decrease, or you experience no change in elevation. Again, this should be number 3. If you get back to the same position where you were, that you started at, your initial height is the same as your final height, so you experience no net elevation change. If you port that over to the idea of gravitational potential energy, the gravitational potential energy of the system consisting of you and the Earth is the same at the beginning as it was when you ended the walk, and there's no net change in the gravitational potential energy. We're going to transport that idea over to electrical potential energy and more generally electric potential. So here are Kirchhoff's rules for analyzing circuits. They're said different ways in different sources. But number 1 is that the sum of the magnitudes of the currents that are directed into a junction equals the sum of the magnitudes of the currents directed out of the junction. However much electrical current flows into a place in a circuit where multiple wires are coming together must equal the amount of current that flows out of that point of the circuit, or else you'd be building up charge or destroying charge or creating charge within that junction. The second one, around any closed loop, the sum of the potential drops equals the sum of the potential rises and gains, and here we're talking specifically about electric potential. So if you measure the electric potential difference across a battery, and you move from the negative side of the battery to the positive side of the battery, the electric potential increases. If you do the same thing across a resistor in the direction that the current is flowing through the resistor, the electric potential drops, and the gain that you experience going through the battery or batteries in any loop has to equal the drop that you experience going through any resistor or resistors in that same loop. So, what's a junction? What's a loop? Well, a junction, again, is a place where multiple wires come together, and a loop literally is any closed path that you can trace in a circuit where you end up back where you started. So if I look here at our circuit that we wanted to analyze, there is a junction here where you have 3 wires coming together, and there's a junction over here. Technically, I suppose you can call a corner a junction where 2 wires come together, but we typically don't analyze that because the same amount of current that comes in here goes out here, and you might as well just treat this as one wire, even though they may be 2 separate wires when you build the circuit. There are 3 loops in this circuit. There's a loop in the top half of the circuit, there's a loop in the bottom half of the circuit, or you can make a loop by going all the way around the outside edge of the circuit. And all 3 of those are legitimate loops to analyze when you are doing circuit analysis. It turns out that when you write mathematical equations to try to figure out unknown quantities, in general, if you have a circuit like this and you write all 3 loop equations, the third equation you write ends up being redundant of the first 2. But there's nothing that prohibits you from writing that equation. And so the general approach that we're using here is to say, when I have a circuit that I identify that I can't analyze with my tools for thinking about series and parallel resistors, I can apply Kirchhoff's rules, and I can write a series of mathematical equations. And my ultimate goal is to write a number of equations that's equal to the number of things that I don't know about the circuit. So this particular circuit right here, there are 2 unknowns, this current going through the 2 ohm resistor and the potential difference across this unknown battery. There's actually a third unknown, how much current's going through the middle of this circuit right here, because we know that 3 amps is coming here, but when it comes to this junction, some amount of it goes here, some amount of it goes here. How much current is in that junction? We're not explicitly asked that in this problem, but you could argue there are 3 things we don't know about this particular circuit. So let's go ahead and do some analysis here. In this circuit, my first step is to label the currents in each branch of the circuit and to designate the loops that I'm going to analyze. Of course, 2 of these currents, I and this 3 amp current, are already labeled for us. So I'm going to only label a current that's going through this middle branch of the circuit. I'm going to call that I2. A comment here, I don't have to know what direction I2 is flowing in. I'm going to guess that it's going to go this way because of the orientation of this 24-volt battery. But it may turn out that I guessed wrong. And if I end up in my analysis finding out that I2 is negative, all that means is that I guessed the direction of the current incorrectly when I started this problem, and it's in the opposite direction to what I diagrammed. Alright, there are 3 loops, but I'm only labeling 2 of them. So this top half of the circuit I'm calling loop 1, the bottom part of the circuit I'm calling loop 2. And I have to decide a direction to process around the loop when I'm writing my loop equation. Again, this is a completely arbitrary choice. You can go either direction. I'm going to go clockwise around both of these loops, but you can just as correctly go counterclockwise and arrive at the exact same solutions. Again, you could also go all the way around the outside perimeter, but we're not going to end up needing that to get to a solution because I'll have enough between 1 junction equation and 2 loop equations to find out everything I want to know about this circuit. So that's what we do next. You can go in any order. I always tend to start with the junction rule, and I'm going to sum the currents that are over here at this left-hand junction. So you can see if you look at the diagram, current I flows through the 2 ohm resistor. It's in series with this battery, so the same amount of current has to go through this battery, and then it arrives coming into this junction. As I've diagrammed it, I2 also comes into this junction, and the 3 amp current leaves this junction. And so the way I write that equation is to say that the sum of the currents coming in, I plus I2, equals the amount of current going out, in this case 3 amperes of current. That's it. I could write a junction rule over here, but it's actually going to be the exact same equation. I would just flip things because here 3 amps is coming in and I2 and I are going out. So now I'm going to use the loop rule to sum voltage gains and drops around each loop. When you do this, you have to pick an arbitrary place to start. So I'm going to start right here at this junction and make my way around the top loop. The first thing that I encounter is the 4 ohm resistor, and I want to write an expression for the potential difference across the 4 ohm resistor. And I could write delta V 4 ohm, but I'm actually going to use Ohm's law because I know 2 of the pieces of information about this. I know that there's 3 amps of current going through, and I know there's 4 ohms of resistance. Potential difference according to Ohm's law is current times resistance. So I have the 3 amps times the 4 ohms to give me the potential difference across this resistor. It is also negative because the electric potential would drop if you move through this resistor in the direction that the current is flowing. Next thing you would encounter would be this 8 ohm resistor, same idea. 3 amps of current through the 8 ohm resistor would be a drop of minus 3 amps times 8 ohms. Going around the loop, nothing on this side. Get here, I have to take a left at this junction. 24 volt battery here. I'm moving through the battery from the negative side to the positive side, so that's an increase in electric potential of 24 volts, so plus 24 volts. And then I move through the 6 ohm resistor with the current I2, so that would be a drop in electric potential, minus I2 times the 6 ohms. I get back to where I started, and the sum of the gains and the drops has to sum up to 0. Let's write a loop equation for the bottom loop. So again, if I start at this same spot and proceed around the loop in the clockwise direction, now in this particular bottom loop I would pass left to right through the 6 ohm resistor against the direction of current I2, so that would be a potential gain plus I2 times 6 ohms. I would pass through the battery from the positive side to the negative side, and that would be a drop in electric potential, so that's minus 24 volts here. I would get to the 2 ohm resistor. I would go through the 2 ohm resistor in the direction of the current I, so that is a drop in electric potential, minus I times the 2 ohms. And finally I arrived at this unknown battery, but I would go through it from the negative side to the positive side, so that is an increase in potential of V. Get back to my starting place, so those all sum up to equal 0. And now if I take account for what I've done, I look and I have 3 equations, and I have 3 unknowns in those equations, I, I2, and V. Only 2 of them are actually asked in the problem. But we've got 3 that we could solve for with these particular equations. Once you've written those equations, the physics is essentially over until you think about the end result. Now it's just math. And there are many ways you can solve a series of equations with a series of unknowns. This one turns out to be easy because one of the equations has only one unknown, and then once you figure that out, you can plug that into another equation and figure out the second unknown and proceed then to figure out what the third unknown is. But sometimes you have, all variables in all equations, and then you have to get creative with your algebra. I will point out that there are online 3 equation solvers and 4 equation solvers and the like that allow you to enter the coefficients in those equations, and it does the algebra for you. We use the first loop equation to find I2, and I2 is right here, but it's the only unknown in that equation. So I'm going to see 3 times 4 is 12 volts, 3 times 8 is 24 volts, so I would have minus 12 volts, minus 24 volts, plus 24 volts, and those are going to cancel each other out. Minus I2 times 6 ohms equals 0. I'm going to move the I2 expression over to the other side of the equation, add it to both sides of the equation, and then I2 is equal to minus 12 volts over 6 ohms, and that comes out to be minus 2 amps. You can have a negative current because all that means is the current is actually opposite to the direction that you guessed it would be. And so I guessed that it would go right to left through the middle part of this circuit. It actually goes left to right, and that's what the negative sign tells me. Importantly, I'm just going to keep it as negative 2 everywhere else I use it because I've set up all of these equations based on my original assumption. The original assumption is wrong. The current is actually going in the other direction there, but it's not going to change anything here in my analysis. Let's see, the junction equation here, now that I know I2, can tell us what I is. So if we plug in here, we get I equals 3 amps minus I2 if you move the I2 over to the other side. I2 we know is minus 2 amps, so 3 amps minus minus 2 amps is 5 amps. And the current is the correct direction that they've labeled on this diagram in I. And there is a 5 amp current going through that 2 ohm resistor. Finally, we know I, so we can go to our second loop equation, or our third equation that we generated here. We now know what I2 is, we know what I is, and this will allow us to figure out what V is. So, it's a plug thing. If I put V on one side of the equation and move everything else over to the other side, I get V equals minus I2 times 6 ohms, plus 24 volts, plus I times 2 ohms. Plug in what we know all of those things to be. I2 is minus 2 amps, and so minus minus 2 amps is positive 2 amps. 6 ohms, 24 volts. I is 5 amps times the 2 ohms, and we end up with a total of 46 volts. So this is a 46 volt battery here in the lower part of the circuit. So a few conceptual questions about circuits before we go back and solve a couple more practice problems with these Kirchhoff ideas. If you have this diagram, what's the correct junction equation for the diagram? Well, if you look at the diagram, I2 is the only current coming into the junction, and I1, I3, and I4, as diagrammed, are all leaving the junction. And so you need I2 to be opposite in sign to all of the rest of the terms, and the correct option for that is option 2 here. I1, I3, and I4 would all be given positive signs. Even though they're leaving the junction, it doesn't matter if you say leaving is positive and coming in is negative, or the reverse. I2 is coming in, it has an opposite sign to the rest. Alright, another one. A battery is used to light a bulb as shown. An identical battery is connected by closing switch S. What happens to the bulb? So if I have this bulb that's lit and I close this switch to bring this battery into part of the circuit, what will happen? The correct answer is that the bulb's brightness will stay the same. There's a certain potential difference from one end of this battery to the other end of the battery, say 1.5 volts if it's a standard D cell. And closing this switch doesn't do anything to change the potential difference across this battery, because it would also be 1.5 volts across this second battery, and the bulb therefore has the same potential difference across it. That means the same amount of current goes through the bulb, and that means the bulb stays the same brightness. A battery is used to light a bulb as shown. An identical battery is connected by closing switch S. What happens to the bulb here? Well, here in fact the bulb would go out if you do this. One way you can see this is to think about the outside loop of this and apply Kirchhoff's loop rule. You would say an increase in potential plus an increase in potential, because you'd be moving negative to positive in both of those batteries, has to equal 0, and the only way you can do that is if the potential itself is 0. So those batteries are actually essentially fighting against each other, canceling each other out, and this would be a terrible circuit to build. You would very quickly waste your batteries, and the bulb would not light in this particular arrangement. Two batteries are used to light a bulb as shown. A third identical battery is connected by closing switch S. What happens to the bulb? Well, previously the potential difference from here to here was 2 times the potential difference of one battery. If these are 1.5 volt batteries, then it would be 3 volts from here to here. And then if I close this switch and bring this part into the circuit, I now end up saying, well, the potential gain across here has to equal the potential drop across here, because that's one loop in this part of the circuit. And so what that actually ends up doing is diminishing the effect of the two batteries. The overall electric potential becomes the average of this one, and so it will be somewhere in between 1.5 volts and 3 volts. Again, not a great arrangement for this, because you're ended up forcing some electric current backwards through one of these batteries, but the bulb will get dimmer. Whether you say it's noticeably dimmer or slightly dimmer is, I guess, a relative question, but it gets dimmer because the potential difference from point A to point B drops when you would close switch S here. Alright, a couple of more practice problems using Kirchhoff's rules to wrap up this discussion. In this particular circuit, we want to find the magnitude of the current in the circuit, the direction of the current in the circuit, and the potential difference between A and B. And this is a problem that doesn't necessarily demand Kirchhoff's ideas until you want to answer question C, because indeed you have one loop, so all of these resistors are actually in series to one another, and you can add them all together. The two batteries are in series with one another. They're flipped around relative to each other, but you could add their potentials as well, and you could solve this using Ohm's law. But we're going to apply Kirchhoff's rules to give us additional practice in writing those equations. So, let's say there's only one loop, and there's no junctions of any significance here, so there's only one equation we can write in this particular place. I'm going to start at the point labeled A and proceed to write my equation by proceeding clockwise around the loop. So the first thing I run into is a 30 volt battery. I would go from the negative side, which is the short line on the battery symbol on an electric circuit diagram, to the long side, so that's negative to positive, so that's an increase of 30 volts. Then I go through a 27 ohm resistor in the direction of the current, and notice again I arbitrarily said I'm going to assume the current goes clockwise around this circuit as well. So that would be a drop in electric potential of I times 27 ohms. Next thing we would encounter would be this 10 volt battery, and you would go across the 10 volt battery from the positive side to the negative side, so that would be a drop in electric potential of 10 volts, minus 10 volts here. Then we run into a 12 ohm resistor. We would be going with the current, so that would be minus I times 12 ohms. Then we run into an 8 ohm resistor. Current is still I, so that's I times 8 ohms. And then we run into a 5 ohm resistor, and that is minus I times 5 ohms, and then we're back to where we started. So those gains and drops all must add up to 0 to satisfy Kirchhoff's loop rule. So we can combine some terms in here. I've got I times 27 and I times 12 and I times 8 and I times 5. That's a total of 52. And plus 30 volts minus 10 volts is plus 20 volts. So I can simplify the equation to say plus 20 volts minus I times 52 ohms equals 0. And then I must be 20 volts divided by 52 ohms, which is 5/13 of an amp. For those of you who eschew fractions, that's 0.39 amps approximately. So that is part A of this. We want to find the direction of the current in the circuit. Well, we already did, essentially. Our answer came out to be positive, and that means that we guessed the direction of the current correctly when we started. If we guessed that the current was going counterclockwise around the circuit, and we did all the equations set up correctly, and we did the math correctly, this would come out to be a negative value, but it would have the same magnitude, and that would tell us that the current would be traveling in the opposite direction to that which we guessed. Now we want to know the potential difference between points A and B, so I'm going to start at A, and I'm going to write essentially a partial loop equation up until B. A noticeable difference will be that I don't expect them to add up to 0, because it only adds up to 0 when I make it completely around the loop. So if I go through A, the first thing I move through is the battery, and I gain electric potential of 30 volts. Next thing I do is I move through the 27 ohm resistor with the current, so that's a drop in electric potential of, well, I can calculate it using Ohm's law, potential difference equals current times resistance. Our current is 5/13 of an amp, the resistance is 27 ohms, that's 135/13 of a volt, or just over 10 volts. And so the potential difference between A and B is then plus 30 volts minus 135/13 of a volt, or 255/13 of a volt, which is approximately 20 volts. One more practice problem. Again, here's a circuit where, because of the two batteries, we can't use our just series and parallel ideas to do the analysis here. We want to figure out what the magnitude and direction is of the current that goes through this 2 ohm resistor. There's really only one unknown we're looking to find, but we're going to have to find some other things along the way in order to work out what the current is through that 2 ohm resistor. Okay, so again, my setup step is to label the currents in each branch of the circuit and label the loops, completely arbitrary in the directions that I assign those currents and the directions I choose to go around the loops. But once I make a choice, I need to stick with that and let the signs in the end tell me whether the currents are in the direction that I chose or opposite to the direction I chose. Okay, so here's loop 1 around the top part of the circuit, here's loop 2 around the bottom part of the circuit, and I'm going to call the current going through the resistor at the top I1. I'm going to call the current going through this middle portion of the circuit I2. I'm choosing it to go right to left because I'm just guessing that it might go in the direction that this battery is oriented. And then I'm going to say current I3 is the current in the bottom part of the circuit. And again, I chose it to go to the right, just guessing that it might go in the direction that this 4-volt battery would naturally push it in the way that it's oriented. But it might turn out that in my solution, one or all of these could be negative, which would tell me that the direction was opposite to what I thought it was initially. Alright, so we use the junction rule to sum the currents at, again, I'm just going with the left-hand junction. I2 is coming into the left-hand junction, I1 is going out, and I3 is going out as I've drawn them. So I have I2 equals I1 plus I3. And I'm going to use the loop rule to sum the voltage gains and drops around each loop. So if I do the top loop, and I start here at this junction, say, the first thing I will encounter is the 1 ohm resistor. I will be going with current I1 through the 1 ohm resistor, so that would be a drop in electric potential of I1 times 1 ohm. Next thing you would run into around that loop is the 1 volt battery, and you would be going from the negative side of the battery to the positive side of the battery, so that is an increase in electric potential of 1 volt. And finally, I would run into this 2 ohm resistor. I would be moving with the direction of the current that I assigned, I2, and so that is a drop in electric potential of minus I2 times 2 ohms. I get back to where I started, so those all add up to 0. Write a similar equation for loop 2. If we start again at that junction, we would go against the current through the 2 ohm resistor, so that term would be positive I2 times 2 ohms. We would pass through the 1 volt battery from the positive side to the negative side, and that would be a drop in electric potential, so that's minus 1 volt. We would pass through the 4 volt battery from the positive side to the negative side, so that would be a drop in electric potential as well of 4 volts. And finally, we would pass through the 3 ohm resistor against the current, so that would be an increase in electric potential of I3 times 3 ohms, and I would get back to my starting place. Those would all sum up to 0. So now it's algebra. I want to figure out what I2 is, and I've got equations that have I2, I1, and I3. And there are, again, many ways you could do this. What I would do is I would say, okay, this equation's got I2, I1, and I3. This loop equation has I1 and I2, and this loop equation has I3 and I2. So I'm actually going to solve each loop equation for the current that's not I2. So if I solve loop equation 1 for I1, solve loop equation 2 for I3, I can then substitute those into the junction equation, and I'll have just a single equation that has I2 in it. So it's just algebra at this stage. Here's loop equation 1. I'm going to move I1 over to the other side of the equation and then divide by 1 ohm to find that I1 is 1 volt minus I2 times 2 ohms over 1 ohm. Well, 1 over 1 would give me 1 amp, and 2 over 1, and they're both ohms, would just give me a 2. So I1 must equal 1 amp minus twice whatever I2 is. Same kind of thing here with the loop 2 equation. I have I2 times 2 ohms minus 5 volts plus I3 times 3 ohms equals 0. I want to get I3 by itself, so I'm going to move the non-I3 terms over to the other side of the equation, and I'll get I3 times 3 ohms equals all the rest of this stuff. Divide through by the 3 ohms of resistance, and I end up with I3 equaling minus 2/3 of I2 plus 5/3 of an amp. And again, if you don't like fractions, feel free to turn it into a decimal at this stage, but you lose some exactness in your answer when you do that. Okay, so now I have two equations. One is I1 equals a bunch of stuff, and the other is I3 equals a bunch of stuff. Those are going to get substituted into my junction equation here. So that will become I2 equals 1 amp minus 2 times I2 minus 2/3 times I2 plus 5/3 of an amp. The next thing you would do would get all the I2 terms on one side. So I'm going to take these two I2 terms and move them over with the other I2. So I2 plus 2I2 plus 2/3 I2 equals 1 amp plus 5/3 of an amp. Collectively on the left-hand side, that's 11/3 times I2. That's equal to 8/3 times an amp. And here actually I've been vindicated keeping the fractions. The 3 and the 3 cancel, and I get something that says 11I2 equals 8 amps. That means I2 is equal to 8 over 11, or 8/11ths of an amp, and that's about 0.73 amps of current that is flowing. Note that the current is positive as I solve it, and so what that tells me is that our initial guess for the direction of I2 was correct. The current is going from the right to the left as it flows through the 2 ohm resistor. This concludes the online lecture dealing with the topic of Kirchhoff's laws for General Physics 2. As always, if you've noticed any errors in the presentation, I would appreciate you letting me know about those. Thanks.